We humans have been curious beings. We have always had a desire to acquire knowledge, and it is this evolution of curiosity that has led to one of the major unsolved problems in physics: the unification of gravity with the quantum and the need for the theory of everything. Hey, I'm Kian, and today I will be talking about searching for the theory of everything, exploring a bit of string theory and some other theories. Okay, so if put literally, the theory of everything is a theoretical framework that explains all physical phenomena. So why haven't we found it yet? Well, there are a lot of reasons, but the main reason is the weirdness of gravity. To understand this, let's look at some of the potential candidates of the theory of everything. Starting with the two pillars of physics, general relativity and quantum physics. In general relativity, the reason of occurrence of gravity is given as the bending of space-time, the fabric of the cosmos. You can think of it as a giant rubber sheet which is bent near objects of great mass. Meanwhile, in quantum physics, there is no bending of space-time. Everything in quantum physics is described by particles. Did you think that there are only 3 particles that make up everything? Not quite. In fact, scientists have discovered 17 particles till date, put together in the Standard Model of Physics, also known as the theory of almost everything. The almost is there because of gravity. No particle has been found mediating the force of gravity, while we have found all the corresponding particles for the other 3 fundamental forces. Seems like they each have their problems and can't be unified. Yet. That is the exciting promise of string theory, where there is another layer of reality itself, and all particles are made of oscillating strings. Different oscillations of these strings produce different particles, including the hypothesized particle of gravity, the quantum graviton. String theory also predicts new, more dimensions. You might ask how this is possible, but the extra dimensions that it is suggesting are extremely small. Here's an analogy of how this is possible. Imagine you are walking on a tightrope. For you, you can only go in 2 directions, forward and backward. But what about an ant on the same tightrope? It can go forward, backward, left and right. It is small enough, therefore it has new available directions to move into. This is just an analogy. But string theory has had a very slow progress with not many new discoveries, but we're still keeping it as a candidate as it solves a lot of problems in physics, and we're hoping for exciting new discoveries in the future. Thank you for watching.